In this lab, we'll be talking about the electric field. This lab has three main objectives. First, you're going to find points of equal electric potential, and it's going to look like a bunch of dots. Then you're going to draw equal potential lines. This is like playing connect the dots. And then from there, you're going to map the electric field. Finally, you're going to get quantitative values for the electric field at different points along your little drawing. We're going to start with a little bit of the theory on the electric field. What is an electric field? So your electric field is the force a positive charge experiences at a certain point. If you were to express this mathematically, your electric field equals the force per unit charge. And again, charge is given this symbol Q. Who knows why? It's historical. So it is the force per unit charge. But how does this relate to the other thing we mentioned in the intro, the electric potential? So your electric potential is the energy per charge. So for every piece of charge you have, how much energy does it take to put that charge there? Now the units of this are the joules per coulomb. Joule being energy, coulombs being charge. However, these also have this other unit of volts, or voltage, which you've heard about. So how does this relate to the electric field? So to start explaining this, let's look at a hill. All right, and let's put a ball on top of this hill, just like it was in first semester. So if we look at this, if you're at the top of a hill, you have a high potential energy. If you roll down to the bottom of the hill, you have a low potential energy. Low potential energy. And if you think about this, the force you experienced in our physics 1 example was gravity. Let's finish that word real quick. Gravity. And gravity pointed down. So this was the force of gravity, which gave you this potential energy, right? Now, keynote, potential energy is in joules. Electric potential is energy per charge. It's a not silly, it's a distinction that can really cause some problems. So potential is energy per charge. So if you think about this, let's draw something real quick. You ever seen a map that looked like this? And we call this a contour map. And each of these lines is an equipotential line. Equipotential. I ran out of room. It says equipotential. So when you look at this, remember this would be like your high altitude, and then this would be low altitude. And if you're reading this, let's put another one right in here. If you're reading this, where your lines are really close together, this is where your hill, right here, or we'll say right here, this is really steep, and over here it's shallower because they're farther apart. So if you have equal potential lines, which is what these are, you will draw these lines 90 degrees, normal to this, and you'll connect this here. Here's a 90, here's a 90, here's a 90, here's a 90. These give you little field lines, or they tell you the force that the particle is going to feel. It's going to feel a force, and a particle placed here would accelerate this way, a particle here would accelerate this way, and a particle here would accelerate this way, from a high potential to a lower potential. So this is what you're going to graph. And when I say graph, I mean draw. So if we look at this, you can say that your potential, and I'm just going to use V for potential, equals your electric field times dx, change in distance. So your change in your voltage, change in potential, is equal to your electric field that you experienced, assuming it's constant, times how far you went. So if you were solving for E at any point in this lab, you would get change in V over change in X. And this is what you are trying to calculate in this lab. So it's how does the potential energy, or in this case, energy per charge, how does your potential change with distance, which is another way of looking at your electric field. And this is a vector because it always points downhill. In this case, there would actually be a negative sign here to keep track of your positives and negatives. So positives would roll downhill. So the electric field is the way a positive charge goes. Positive charge would go downhill, which is why that's there. All right, let's look at our apparatus. So to start this off, you're dealing with conducting paper, tack it down on all four corners, and this is little silver ink. Okay, these would represent perfect conductors, which you're going to plug into the battery, and you're going to use this meter. So a couple notes about this meter, and these are very important. First off, this dial, see how that's on 3 volts? That is the max voltage that you can read. So if you're doing real small measurements, use 1 volt. If you're using big measurements, use 3 volts. And then to get to 6 volts, which would be 4 batteries. By the way, each battery is about 1.5 volts, but you're looking for potential lines, so that doesn't matter. Sorry. When you're looking for the 6 volt line to start with, use 10 volts. When you're looking for 4 volts, use 10 volts. When you're going to 3, 2, and 1, use this 3 volt line right here. Second important thing about this apparatus is you see this mirror right here. Make sure you are always, with any instrument, look straight on, which means that you will not see a reflection. No reflection in that mirror. All right, if you can see a reflection, it means you are not looking directly at it. So let's watch how this thing works. You were going to put on a probe. There it is. And you can see when you touch it, the meter starts going up and down. Again, make sure you're looking directly at it. And you are going to make a dot every time it gets, every time that it gets right in here, you'll just make a little dot wherever you see a line. Always push with the same amount of force, otherwise it can cause jumps in the needle. So you're just going to make a big connect the dots. When you're done, it looks a lot like this, and you can see these would just be the dots, and let's say that this is a 4 volt line, this is a 3 volt line. So what you're going to do after you have these dots is you are going to connect the dots, and you can use different pieces of colored chalk. That's why they're there. And you'll get a 4 volt line and a 3 volt line. These are your equipotential lines. So these are equipotential lines. So now what you're going to do, let's say we've got a 3 volt line here and a 2 volt line. You're going to draw electric field lines perpendicular. So here's perpendicular to this spot right here, perpendicular to this spot, perpendicular, 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 perpendicular. Because electric field is perpendicular to your electric potential lines. So we would draw it this way. And in this case, the positive charge goes downhill. So you can go ahead and put the arrows. So the important thing is to draw the lines perpendicular. Electric field lines, these are E, perpendicular to your equipotential lines that you drew before. The final step is to measure, because if you're using the formula where E equals negative change in potential over change in X, you need to know what delta X is. So to get your delta X, you measure from here to here. These metal rulers are a little flexible, and again, do not measure from the end, and always take multiple measurements. Also, don't bend these rulers too hard because they can stay bent, but always get multiple measurements. That way you can get your error bounds. So your error analysis, if you're using E equals change in V over change in X, you'll have a plus or minus up here and a plus or minus on here. This error from multiple measurements, and this, well, you can take multiple readings, but that would leave dots everywhere. So this is going to be from the accuracy in the readings of this. So the wrap up. Draw equipotential lines. This looks like connect the dots. Then draw your electric field lines perpendicular to the electric field lines and calculate the electric field in a number of times specified in your lab handout. And also mark where E was found. All right, you need to tell me where you measured the electric field. You can't just pick it. By the way, you could also use delta V as 1 volt. You could go 2 volts. You can find a really long field line and calculate the average electric field. So you'll repeat this for both patterns. That's important. Both patterns. And both patterns are going to use the exact same process. Just be very careful and work slow. And when you're done, you'll have a nice pretty picture and hopefully some knowledge of the electric field. And I'll see you in lab.